functions and servers, as well as they can be provided inline by the traffic probes and monitors. These are getting popular. For example, telemetry getting popular. We can also collect data by DPI, deep packet inspection. Okay, that was the background on network analytics. Next, let's see some of the standardization activities going on ITU and 3GPP HT. ITU started working on machine learning in networks long ago, about 5-6 years ago, and it has already published several recommendations. Actually, ITUT recommendations are the standards developed by ITUT, so they are called recommendations. Let's cover some of the recommendations. First, let's start from Y.3172, which is the architectural framework for ML in network. So this figure shows the framework. It includes 4 major components. On the bottom is the underlying network. It is actually the virtual network on the virtualized platform of the network. This provides monitoring data, as well as it accepts commands from the machine learning based control subsystem. So above the underlay network, there is a machine learning pipeline subsystem. It includes the machine learning processes or the functions to process the data and make a decision on the control. And this machine learning pipeline subsystem gets machine learning models from the machine learning sandbox subsystem. It is the training place for the machine learning models. So they get data from some simulated network, and the models are trained before applying for the control of the real network. And the overall control is being managed by the management subsystem, which can get machine learning intents and usage in the machine learning function orchestration, and to decide how they can control the machine learning models. So this is the overview of the framework designed by ITU. Next is Y.3173, which is the framework for evaluating intelligence levels. As we know that applying machine learning or AI to the networks would be making the network more intelligent. So intelligent means that most of the control functions would be carried out automatically rather than requiring human intervention. So this is the recommendation which provides a guideline for evaluating the intelligence level. An intelligence level can be evaluated in terms of various dimensions. This ITUT recommendations has identified 5 dimensions: demand mapping, data collection, analysis, decision, and action implementation. This demand mapping is something like the rule definition or the intention provided to the network to perform something autonomously. And in terms of the subsystem, we have we can automate the functions of the subsystem, like network element management system or network application platform, as well as we can automate the workflow processes: planning, deployment, maintenance, optimization, and service providing. So these workflow and the subsystem can be automated in terms of the various dimensions. So based on whether those dimensions are performed by human or machine, we can identify the level of intelligence. For example, let's see, the current networks are called in intermediate intelligence level because most of the action can be implemented by system. The system can also collect data, but in order to analyze the data, we need some human intervention. Similarly, to make decision, we need human intervention, and of course, for the demand mapping or for the rule definition, human intervention is required. So we are in current level 3, and in case we have full intelligence level 5, everything would be performed by system. So we have been doing research and development for leading to level 5 intelligence. Next is architecture framework for AI-based network automation and resource automation for resource and fault management. As we know that resource management is the major issue, and also fault management is the major issue in the virtualized network. So there is a recommendation, and this recommendation has been developed based on our contribution from our research laboratory. It is based on 3172 framework that I showed you. So what it does, it collects the data, it analyzes the data to determine where the fault has occurred or where the resource is not being sufficient. Then it performs some action. Action can be arbitration or the network function migration and the reconstruction of the network. And the action decisions are provided to the controller, and controller accordingly controls the underlying network. So this is the framework. This framework includes both the failure detection and recovery mechanism. And when we do the recovery, of course, we have to know how to manage the resource, how to adjust the resource. And in order to identify the failure or root cause analysis, we have this learning phase and operating phase, where machine learning models are trained, evaluated, and then optimized. And next, I'm going to cover one or two standards network data analytics functions being developed in 3GPP. So popular one is architecture enhancement for 5G to support network data analytics service, which is TS 23.288. It provides a framework for the data analytics. Here is the framework which can collect the data from the network function, application functions, and which does some decision making for the control and provides the control decision or the results to the underlying network. And in order to do the data analytics, it uses the data repository. Maybe these are the requirements of the application services or the various intent from the users. And then there are also operation and management, operation and maintenance component, which provides guideline to the network data analytics function. So this framework is also similar to the framework being developed by ITU. Next is the framework developed by ETSI. It's also a standardization body in Europe. The popular one is Zero Touch Network and Service Management Framework. It is what it is doing. It's also assuming existence of multiple domains in the underlying network, multiple network domains, and from each domain, the network data is collected. It says the management data is collected and being analyzed, and then the analyzed result can be provided to the end-to-end service management domain, where the data obtained from different domains, because it assumes that in order to provide end-to-end service, different domains may involve, and we need to have integrated analysis of the data. And based on the data analysis, it can provide the analytics results to the underlying domain, and the domain can be controlled. So this is the concept defined by JET-SM framework. So the major components are data collection, analytics, intelligence, orchestration, and the control. So these were the background on standards. Next, I'm going to show you some of the research we have conducted in our lab. The first one is a network or the server virtualization and autonomous resource allocation. As we know that virtualization network platform has allowed us to create virtual networks for different types of services. I mean the virtual networks with different quality of service providing capabilities. So if we talk about 5G network communication types, we may have the broadband communication requiring high bandwidth. We may have the real-time low latency communication services requiring, of course, very low latency and reliable communication. We may have massive machine type communication, which require connectivity to a massive number of devices. So all these services can be provided over the same physical infrastructure by configuring different types of virtual networks. So when we do this type of network configuration, we need to have some sort of autonomous and predictive resource allocation mechanism. And for this purpose, as we have been using machine learning models, it's very clear. But there are some problems, like no machine learning single model is good enough for all type of problem solving. For example, let me show you in the other slide. We may have a support vector type of regression to predict CPU usage per second. This support vector machine or regression has the beneficial feature of higher speed training, but their prediction accuracy is lower. Similarly, we may use LSTM, long short term memory. They have higher prediction accuracy, but they require longer training time. Similarly, we may use use other regression models of the lasso, which provides higher prediction accuracy with a smaller amount of memories, but it's not suitable for predicting per second or prediction in real time. So these are the issues we have been facing with different types of models, and none of them is suitable for all requirements. So that's why what we have been doing research is to develop some sort of framework where we can choose the optimal machine learning model for the given network condition or the requirements. For this purpose, we have formulated a framework in which machine learning repository server is there, and this server is collecting data from the distributed machine learning engines, and it's regularly monitoring whether the distributed machine learning engines are optimal or not, whether the underlying network conditions have changed or not. And if the underlying network conditions have changed a lot, the previously deployed machine learning model would not be optimal. So it has to be retrained, or it has to be sometimes replaced by another model. That work has been done by the repository server. So we have been conducting this research, and we have found that by the dynamic update of the machine learning models, we can have better training accuracy, better accuracy, prediction accuracy, as well as we may take less time to do the updates and the retraining. And this paper has been published in recently in IEEE norms. You may download and check it. There are other researches being done on the same area. This one is not from our lab, but somehow related. Artificial intelligence enabled intelligent 6G network. So it says that artificial intelligence can be applied in different places, from device layer to the application layer. So these are shown here. If you are interested, you can look at the paper. And similarly, a digital twin network framework is being very important in order to automatize the network control, because digital twin network provides the global view of the physical components in the digital space, and we can do like the prediction for long term. We can do also simulation for the scale, and then provide control. So digital twin network framework is being developed in ITU. This one is the very high level framework, which is ITU TWIDER 3090. If you are interested, you can look at the document. Okay, thank you very much. This is all about my presentation.
Thank you, Dr. Kaple, for presenting your work on AI and data analytics for network service management orchestration. Is there any question from the audience? Doctor, I will ask one question. I would like to know whether you have also considered reinforcement and deep reinforcement learning algorithms in your repository server as well?
Yes, we have been considering those as well. DRL are I think the major components, but in the evaluation table, we have not shown here. We have used it for the individual network control. For example, in the machine learning, let's say engine A or engine B, we can use DRL. But in our evaluation, they can be used individually as well as collectively with the others. Yes, we have used it, and we have also paper on it. If you check our publication.
Thank you very much.
Yes, thank you so much.
Someone wants to ask a question. I
just want to view the last slide of the related work to the AI networks.
Okay, let me share the slide. You mean the last slide, right?
That's not from your lab.
This one or this one?
I think this is the last.
Yes, this was the last.
They don't have a mic.
The previous one.
Yes.
Yeah, this one.
You mean? Would you please repeat the question? I couldn't get the question.
I just want.
I think they just want to take a picture.
Yes, this is published in IEEE network in 2020. The paper title is shown here, so you can get a more elaborated version from the repository. Thank you.
I hope there are no more questions. So thank you, Dr. Kaple, for your presentation.
Yes, thank you so much.
Yes. With this, we'll go to our next presentation, which is by Janki on their work on Agent Q from China Telecom Network Large Model.
Okay. Is my voice okay?
Yes.
Okay. Let me share my screen. You see my screen now?
Yes, we can see.
Let me use the presentation mode. Okay. Hello everyone. Good morning. I'm Zhang Ke. I'm from China Telecom Research Institute. My personal area is cloud and network autonomous operation, customer experience management and assurance, and related standardization works like in ITOT and TM Forum. So I would like to spend the next couple of minutes to share with you the latest adoptions of China Telecom Network Large Model. We also give it a name Agent Q. So far, autonomous operation have become the transformation strategy of mobile operators. It is also the key features of China Telecom Cloud Network Integration version 3.0 strategy. By the way, the key to version 1.0 is the cloudization and the virtualization of the network. And the key to version 2.0 is the cloud network collaborative orchestration with network as the basement and the cloud as the core. This is a process of our cloud network autonomous operation practice. You can see in 2019 to 2020, China Telecom began to define cloud network integration blueprint, and in 2021 we started to develop autonomous operation relevant standards in SDOs like in ITOT and TM Forum. In 2022 we evaluated autonomous level in some certain areas, in some certain domains, and in 2023 last year we expanded the scope of the evaluation into 7 network domains and over 8 network product. The average level of all the 31 provincial companies of China Telecom is level 3.0, and this year our target is continuing to improve the autonomous level and fully achieve level 3.5. We define 3 ultra premium customer experience, ultra fast telecom services, ultra intelligent cloud network operations as the vision of our cloud network autonomous operation. Just like the grading for car autonomous driving, there are 5 levels to evaluate the situation of our autonomous operation. We are now in the transition period from level 3 to level 4, and we expect to fully achieve level 4 by 2025. And the end goal is level 5 by 2027. In the process of to achieve cloud network autonomous operation, we have faced many challenges. Current manual operation is unable to meet the requirements for operation and maintenance. It is necessary to start from the operator's perspective, including user service requirements such as the accurate service provisioning, network operation and maintenance requirements such as network fault troubleshooting and fast response to leverage a large language model to build a framework which adapts to complex cloud network operations in the future, and eventually to meet the high-level evolution requirements of autonomous operation. AI, especially GenAI, is the key method to address these challenges. GenAI it is no doubt the hottest research area so far, right? It has risen from just AI-based content creation tool to strategic platform, rapidly becoming one of the enterprise strategies for global operators. We have referred to some research report of telecom industry. Here are some points. You can see here, over 50% of the interviewed company they already have a specific GenAI strategy, and they have already made good progress. And most of the interviewees agree that within 1 or 2 years, GenAI will significantly improve their operational efficiency and reduce operating costs. And totally 7 families of GenAI use cases are categorized, in which customer operation and the network as the most widely embraced. And also, we are also working on it. China Telecom officially released the Agent Q network large model in September last year. It is also the first formal network large model in the world, we believe. Agent Q focuses on telecommunication domain, covering 5 typical scenarios, including network planning, construction, maintenance, optimization, operational decisions. Its advantage include a domain-specific user intention recognition, a general LLM, large language model, logical orchestration, collaborative scheduling, and advanced predictive analytics. Additionally, it offers MaaS, model as a service, must for internal and external users or customers. So AgentQ, it's a specialized large model in network domain, which is built by learning domain-specific knowledge and characteristic data of the telco industry based on a general large language model like ChatGPT. Network large model can provide reasoning services through APIs or chatbot. For example, you can ask, hey, give me a briefing of the running status of the core 5G core network in Beijing yesterday, and tell me the anomaly root cause analysis, right? So obviously, a general LLM like ChatGPT can do that because it does not have the knowledge or corpus in this area, right? But a network large model can do that. And of course, the similar process can also be used to construct the other industrial LLMs like in financial areas, in education, and in healthcare. Here's some key milestones of AgentQ. In June last year, AgentQ was kicked off and we made the first demo. And in September last year, the first version of AgentQ was released. In the following 6 months, we have released 7 co-pilots, and all the 31 provincial companies, staffs of China Telecom can use them. And in the World Telecommunication Day this year, we released Broadband Agent. We believe that the AI agent represents the most advanced form of the future network large language model evolution. So by the end of this year, we expect to offer totally 12 co-pilots or AI agent application for all the 31 provincial companies. This is a full picture of AgentQ cloud network operation scenarios and the progressive evolution of our AI capabilities. You can see in this slide that there are 3 stages of AgentQ applications. The first one is Knowledge Copilot, which can provide easy access to cloud network domain specific knowledge pilot, which is AI helper in production for cloud network staff or cloud.
I think there was some issue with the network. Can you?
I'm sorry. Did I get offline just now?
Yeah, it was. Yes.
Is it okay now?
Maybe. Yeah, it's okay. Can you please share the screen again and slides?
So, did you hear this slide, the key milestone?
Yes.
Okay.
Yes, it was okay.
Okay, so I will continue with this slide. Okay, my point is in the third stage of this evolution, AI agent. What you need to do is just telling the AI agent your target or your problem, and the AI agent will understand your intent and realize the task decomposition, orchestration, execution, and the validation fully automatically. So from you can see that from a knowledge copilot to operation copilot, and finally to an AI agent. This exactly represents the evolution trend of network LLM towards more efficient, more automated, and more autonomous. I can show you more details about LLM-based AI agent framework and our key innovations. I like this slide because it not only shows how AI agent works, but also explain its position in the whole network large model solutions. AI agent is here. On the northbound interface, customer can use large model reasoning service. The AI agent will understand the user's intention and realize the task decomposition, business flow orchestration, scheduling, and the task execution internally. On the southbound, a general LLM is the foundation model. Our foundation model parameter scale might reach 72 billion. We use network domain specific corpus for incremental training of this LLM. The corpus are prepared from offline knowledge, the headquarter, and the provincial company database, and third-party database. Then we got a network large model. Through fine-tuning, we further obtain scenario A large model and scenario B large model, etc. Scenario refer to those network relevant business scenarios that I mentioned just now, like planning, construction, operating, optimization, etc. AI agent can call large models through multiple rounds of dialogue on the southbound interface. Furthermore, we also use retrieval augmented generation RAG technology to enable a customer to get the expected result more accurately and more efficiently. And of course, during the whole process, when using all this AI system or GenAI technology, we've placed a high a priority on adhering to ethical and responsible AI principles, complying with national laws and operator-specific regulations, and revised measure ensure the security of personal data, adhering to strict privacy principles. Next, I would like to show you two use cases of AI Agent Q. The first one is a home broadband self-service AI agent. We have embedded this AI agent interest into our home broadband service app. It will create automatic troubleshooting process based on a large model, combining intention recognition and accurate solution recommendation and improve the self-service success rate. You can see in this slide that the home broadband users tell the AI agent, hey, I cannot access the internet, or the internet speed is very slow. Then the AI agent will query all the APIs, both from BSS domain and ASS domain, like the account consistency from the product subscription data, and whether the customer has the charging issue, and the optical modems status check, the port check, the light attenuation check, etc. On the other hand, we use RAG technology to offer the network large model the fragmented home broadband domain-specific knowledge or data. The reason that we call it fragmented because all these data are not well organized. They are scattered in the forms of operation manuals, a troubleshooting guide, use case documents, some data from the website or forums, or even the work order system database, right? So we call it fragmented information. And AI agent will generate a prompt to call the network large model to generate the final diagnosis handling plan. The network large model will decide the process and the final solution based on the historical record or the domain-specific knowledge, and covering all the possibilities. So this decision process is no longer based on a static decision tree. It is also not general SOP. Actually, it's an accurate, personalized solution based on this individual customer's real data and conditions. And of course, we have a bottom lines plan. In case that the network large model cannot, the output result of a network large model cannot solve the user's home broadband issues, and of course this really happens, or it has the hallucination problem, we still can suggest the HVB users to turn to the home HVB hotline or website for help to realize the closed loop of this end-to-end process. So this AI agent can quickly respond to users' need, improve service quality, and increase the user satisfaction. Just in one single province, two companies of China Telecom, this HBB fault resolution efficiency is improved by around 30%, and the annual operation and maintenance cost can reduce by $2 million. The second use case is about the radio network optimization copilot. The whole process independently generates a high precision wireless style list, root cause, and the optimization plan, and creates full domain digital network optimization expert, which is embedded in the production system of the provincial company of China Telecom to assist in analysis and decision making. This copilot can offer minute-level troubleshooting, effectively improve the efficiency of intelligent identification of the network performance or quality issues and service quality problems, and realize the accurate locating of the problems, automatic generation of work orders, or etc. And the accuracy is about 90%. It can also offer intelligent generation and evaluation of optimization scheme. The radio network Q&A robot can support multiple round of Q&A in radio network optimization scenarios, and the Q&A success rate is expected to over 80%. So as a summary, we will warmly welcome and look forward to collaborating with all the experts present in the future. For example, the AI Ops, AI Agent, ODE Catalyst project in TN Forum, and AI Tom, Knowledge Graph, knowledge center, network, large model, relevant topics, or project in ITOT. You can see in this slide on the left is the ongoing project or standards in AI Ops project in TM Forum. We have already a series of deliverables about AI Ops service management process and the AI Ops system components or module functional architecture. On the right is the ongoing intelligent management related network management related project in ITOT like SOMM or an AI Tom. So if you have any comments, questions or suggestions, please feel free to send me an email. Okay, that's my sharing today. Thanks again for having me here. Dr. Mohammed?
Yeah, thank you, Yanti, for your valuable work, presenting your work on Agent Q. So, is there any question from the audience?
Hello. Hi, Jankha. Actually, I have two questions.
Yes.
I have two questions. Can you please move to slide number 13?
13. Let me share my screen again. This one or this one?
No, the next one.
This one?
Yes. So in this, I was just wondering to see the estimated effectiveness, and you have mentioned the 80% accuracy. So do you think that 80% accuracy is enough?
Frankly speaking, it's not good enough, right? 80%. Let me check. You mean the Q&A response rate, 80% success rate, right?
Yes.
Yes. Frankly speaking, 80% is not good enough, and it has still to be improved. But what we're trying to do is that my point is that it's in the just the beginning of our practice to implement AI agent to several multiple network domains. So in the first period, the first stage of this work, maybe success rate about 80%, 90% is acceptable. But we still have a lot to do to improve these indicators.
Okay. So this
And of course, as I mentioned just now, we still have some backup plan or a bottom line plan that in case that you cannot get the answers or get the solutions by AI agent, you can also turn to some the real people, the customer service representative or call center hotlines to get the final help from the traditional way.
Okay, all right. So the second question is, in agent-based AI, is there any involvement of a human? Because sometimes in our network we have some problems which can be only solved by a human. So what do you think about the involvement of a human in agent AI?
Yes, I think the answer to this question is similar with the last question just now. And let me turn to previous page. Yes, ideally, we indeed hope that in this whole process of this AI agent solution, there's no need to let a real person, let a real people to attend this process, because from the general LLM training, from the domain-specific corpus preparing, and from the incremental training, fine-tuning, if all these preparations are done, the AI agent and the network large model can fully automatically realize the whole process from the beginning of the user's intention recognition and the task decomposition, orchestration, and validation fully automatically. The ideal condition is that, but the reality is there might be some like the hallucination problems by the AI agent. Sometimes maybe he cannot solve all the problems of the customers. So that's why we need a backup plan or bottom line plan to finish to ensure the basic service for customer. But the evolution trend, the future, the ideal condition is that this whole process is fully automatically.
Okay, thank you so much.
Thank you.
Out of curiosity, I would just like to ask, what does this Q stand for in Agent Q? Is it for Q learning algorithm from that, or it has some special meaning?
You mean, Dr. Mohammed, you mean the letter Q?
Yes, in the Agent Q.
Not that complex. In fact, Q is the beginning letter in Chinese, Qiming. Qiming means the ignition or a good beginning of that. So we just
Right.
use this
Thank
method
you.
to yeah.
Okay, thank you once again for your presentation.
Thank you, everyone.
Yeah. Okay, with this we'll go to our third presentation, which is by Mazahir Hussain from Korea Institute of Science Technology Information, and he'll present his work on HPT collector, which is leveraging high performance parallel processing to optimize AI applications for networks.
Can you hear me?
Yes,
My screen is also.
yes, visible.
Hello everyone. My name is Mazahir Hussain. I'm a PhD student at Korea University of Science and Technology, and I'm also a student researcher at QNet Center, KISTI in Korea. So today my presentation is HPT collector. It's more or less than AI, but it would be one instance towards AI applications using parallel processing. So with that I would like to start. So the presentation roadmap is that I will go in deeper into the HPT collector, what it is, and the background research about it, and then also the architecture implementation, followed by the results, and also I will shortly present what's our current research, and then I can conclude in my presentation. So what is HPT collector? Basically, HPT collector means high performance telemetry collector. As we know that network monitoring and network telemetry is very important, and it plays crucial role in understanding the infrastructure of network, right? What's going there, and to do so many other things like troubleshooting, load balancing, and fixing some problems. But the problem arises when we can see that for network monitoring or network telemetry, we use simple tools to the advanced tools, like even we use ping for, that's also a network monitoring simple tool to check the connectivity, and as well as like a trace route to find out the routes where the packet went through. So and Argus flow, NetFlow, those are the tools we use in network monitoring and telemetry system. But those tools are not good enough for when the telemetry system, when the network infrastructure speeds goes beyond 100 Gbps. Like for ISPs and for network research and education network, there we suppose like more than 100 gig of supports. So we would like to, we proposed a solution for that, to for collecting those telemetry data. We call it HPT collector, where we are using parallel processing techniques to maximize the performance of that system. So before going to the architecture implementation, I would like to present what's the background and related work. So for packet processing ASICs, there are two main categories. That one is top-down approach, and then second is bottom approach. In top-down, the vendors gives you some set of protocols, that these are the protocols, you can use it, and we cannot program beyond that. But in bottom-up approach, like PISA architecture, one of them is protocol independent switch architecture, like for Tofino, which from Intel, which also called the white box switches or white box network devices, where we have the flexibility to program our own code, our own protocol, using different programming language like P4 programming language, like where we can write our parsers, how the packet will be parsed, and we can write our match action controls tables, and then also many other constraints we can define there. Also, when it comes to kernel, how we process the data, process the packets at the kernel. If we talk about the fast packet processing, we can understand that there are two techniques, like in kernel processing and kernel bypass. In kernel processing, where we use eBPF XDP, or the BPF is virtual machine where eBPF program, we inject that program into the kernel space where we compile it and then verify the code, object code, and then once it will be verified, it will be injected to the kernel and it will not crash the kernel. That's the beauty of the eBPF programs. And the second one is the DPDK, where we bypass the network stack of the kernel, and but it also where we also have to sacrifice the security features which is provided by the Linux kernel. For network telemetry, there are three main categories. Researchers are researching, creating in-bin network telemetry system-based architecture, and also the sketch-based where we use probabilistic data structures, what packets we want to mirror and collect, and what we want to skip. And also there are researcher, we can see that it's based on RDMA. Instead of processing the packets, we just directly store the packets into the storage system using the RDMA protocols. Where we just bypass the CPU processing. And so in HPT collector, we follow the few principles for high scalability, performance, security, and portability. We wanted to have a scalability where we can increase the performance with the number of cores. As we increase the number of cores, the performance must be increases. And the security, we wanted to use the security features provided in the Linux kernel. Also portable, if we want to move our program to another kernel version or another distribution of the Linux, then it would be easily work there. So with that, I would like to explain the architecture of the system, the HPT collector. Is there are different components of this system has. First is that programmable switch. We are using Tofino P4 for P4 programming language, where we wrote a program for mirroring the packets and then creating a telemetry packets by prepending the metadata of that telemetry data from the switch, which ingress port it used, which egress port it used, what was the in-queue depth, what was the dequeue depth at that time when the packets came, what was the timestamp when the packet come, what was the timestamp when the packet leaves, so we can understand how much time a packet spent on each control, like ingress, egress, or whole processing, whole control. And then we are sending that packet to the HPT collector server, basically, where we are using eBPF, a BPF program, and with the XDP framework. XDP framework, it's a framework for capturing the packets earliest as possible before it touching the network kernel, basically. So it minimizes the latency. And we also used BPF ring buffer. Ring buffer is a memory buffer which shares between Linux kernel and the Linux kernel and user space. And we have also used another library called OpenMP for parallelizing the processing of the packets. So the implementation details is that first we used a single core user space application in the eBPF program, where we in the XDP program, we can see that it uses eBPF ring buffer, which is eBPF ring buffer itself is a multi-producer single buffer, single user or single consumer buffer. So where we can we can write many from many cores, and then we have to consume by one core only. So in this case, we can see that the result is decreased as we increase the IRQs, where the packets are stayed into. as we increase the IRQs, number of cores, the performance decreases because of the contention at the ring buffer. So we checked using flame graph. Flame graph is for profiling the CPU utilization at different user space as well as the kernel space, where we understand that the CPU utilization is divided in two parts. One is using the IRQ, soft IRQ, and then second is our program itself, the eBPF program. But that means our IRQ is taking a lot of time, spending a lot of CPU resources. Then we move towards another approach that instead of single ring buffer for multiple IRQs, we use array of ring buffer, where we assigned each IRQ to a different ring buffer, where each IRQ, each core is writing into different. It's violating the main principle of the ring buffer basically, but it's started to give a better result for that, where we can see that instead of 2.6 we started to get 2.67 as it reduces the CPU contention there. But the problem was that our at the user space side, our program is using only single core, so it first consume all the packets from the first ring buffer, and then it goes to second, third, and so on. In this case, all the other the ring buffers will be filled, and it will have to wait there. So but when we checked the flame graph, where we used profiling of the CPU, there we understand that all of the CPU resources are consuming at the IRQs instead of doing something which is important, that processing the packets at user space, in this case, like 92% of the time is spending without producing enough processing packets there. So then the third approach we move towards is that we steer the packets to each different IRQs, and then we assign that IRQ to different CPUs, and then different BPF ring buffer. And also each ring buffer is consuming by different threads instead of one thread, one thread consuming all of them, but it's now using parallel processing technique. So it's consuming, it's like the packet is coming at the first one for the IRQ one, and it's going to the thread one, and then second packet is going to the core 2 IRQ2, which is consumed by thread 2. So in this technique, we check the flame graph. The flame graph shows that now the CPU consumption is completely converted to the eBPF program, what we wanted to, where actually the packet processing is happening, and the IRQ is decreased by 4% as it doesn't need to interrupt again and again, because it's in the pool mode, so it's consuming with the fast as possible, so it does not need to interrupt again and again, so which reduce the time at the IRQ side. So for evaluating this system, we created a test bed where we used a P4 switch, P4 Tofino 1 switch, and then.
Thank you, Mazahir Hussain, for your presentation once again. So with this, we'll move to our final presentation of this session. This is from Dr. Yawar Abbas Bankash from National University of Sciences and Technology, NUST, Pakistan. And he'll present his work on SDN and fog-based IoT application challenges and way forward. So, Dr. Yawar, you can start, please.
Yes, hello everyone and good morning. Thank you very much, Dr. Afaq. I hope I'm audible.
Yes, thank you.
All of you.
Yes, you can start, please.
Thank you. So, Dr. Yavar here, Associate Professor from National University of Sciences and Technology. The topic is about the integration of different technologies. It is not going to discuss some research article, but just to give you the integration of some different technologies and some challenges and way forward. So it is all about the SDN fog-based IoT applications and how we can integrate SDN and fog-based IoT application together, and what are their challenges and way forward. So this is just a brief outline. Internet of Things, definitely we will just throw a little light over the Internet of Things, and then fog computing, then IoT and SDN. And at the end, we will discuss some different architecture related to SDN, and then the conclusion. So all the times we are just listening this term IoT, IoT, IoT. You know that these are connected devices, and the philosophy of the IoT is whatever is going to be connected should be connected. If there is any possibility of anything to be connected, it should be connected. So this is all about the IoT. It means that, for example, if we have any device, and then there is a discussion that can we say that PC is an IoT device or not? Because as we say, the philosophy of the IoT is anything that is possible to be connected to the internet is to be connected if there is a possibility. So definitely PC has the possibility to be connected to the internet. So the same way server has the possibility to be connected to the internet, but from the environment, and they are uploading their data to the upper layer, and in the upper layer we are having some processing power. And at the end, we have the different applications. For example, that application might be related to health, that application might be related to some medical, that application can be related to agriculture, that can be related to industry. So this is just the broader overview of the IoT architecture, but definitely we have the 4-layer architecture as well, and at the same way we have the 5-layer architecture as well. But for the sake of the understanding of the IoT, fog-based computing and SDN, I'm not showing the 5th layer, the 5-layer architecture as well. I don't think so it is new for all of you, because you are almost coming across all these different applications in the IoT devices, but just for the sake of setting the background for our further discussion. As you can see that now we are in the second technology, that is called the fog computing. But before we dive into the fog computing, definitely we just know the cloud computing. Computing is, of course, the processing. So the cloud computing that you cannot achieve, that you can achieve through some internet connection, where your device that is just connected to the internet, and there is a processing on the other side of your area, and that is called in the broader spectrum, that is called the cloud computing. But as we are progressing, as the humanity is progressing towards the artificial intelligence, towards other technologies, so the same was the case here, because we are having some delay sensitive applications. We have so for those delay sensitive applications, it is not necessary to move all your processing power to the cloud. So there is a fog in between the cloud and in between the sensors. So that's why this terms coined that there's a fog computing. So as you can see that there is a cloud, and then there is a fog, and then we have the IoT devices. It's the same IoT architecture, but right now we have added another layer that is called the fog layer. So definitely we have some applications that we included this fog layer inside, in between the cloud and the IoT device. And there is another term that is called the edge computing, and as evident from its definition, that computing which you incorporate just at the edge of your network, not crossing the border of your network, but at the edge of your network. Definitely we are not discussing the edge computing today, but that is also a term. So we have 3 terms. One is called the cloud computing, another is called the below layer is the fog computing, and the lowest layer is the edge computing. We have many applications. The most delay sensitive applications, for example, that will be definitely carried upon your own device, but definitely we are connected, and without connection, without that communication, it is difficult for us to achieve the goal, for example, of the internet of vehicles. For example, if you are using some application for vehicles, so there will be connection. If we are using some devices, if you are using the exploiting the application of medical sciences, we need network. So definitely it is not the case that each and every time we will be processing those things on our own system. So you are just moving one step above your system, and that is called the edge. But there is a possibility that you do not have the capacity, you do not have the capital expenditure to invest or invest much money on to buy your own devices. So then you go on the fog layer, and at the end, for the extreme critical cases where you do not need to have all those big data centers, all those big providers, so at the end we have the cloud layer. Here, as you can see that in the very lowest layer, we have edge devices, and as its architecture says, we are in billions here. Here we are not in billions, but we are in millions, and here we are in thousands. So architecturally, the concept is same, but the how you deploy those things, that is different. So that's why we have different architecture for the cloud, we have different architecture for the fog, and we have different architecture for the edge. Although the purpose is the same, to provide the services to the end customers, to the end users, but for the edge side, we are having those services in the extremely delay sensitive applications, and here is not that much delay sensitive application, and here we can tolerate some more delay. So the more critical sensitive application, we use this edge computing, and less critical and more less critical, we use the fog and we use the cloud. These are some parameters that we can differentiate that why we use the edge computing, because if someone asks the question that what are the different purposes of the cloud layer or the fog layer of the edge layer, so I think these are the answers for those different questions. Now fog-based IoT, so definitely, because in the fog-based IoT, the most important point is we should not go to the cloud each and every time, because if you are sending your all requests to the cloud, and from the cloud if you are receiving those requests, so definitely it is a delay, it encounters much delay, and in networking 3 millisecond, 5 millisecond, these delay, they have big impact as compared to, because we human being, it's impossible for us to perceive 3 millisecond or 5 millisecond delay. Yes, it is possible for human being to perceive 0.4 second delay or 0.5, 0.6, but for the systems, for the computer, even 10 millisecond delay is a big amount for the computers. So here, just imagine if there is an application and that is extremely sensitive application, or we say that it is related to the vehicle to vehicle application, V2V. So in the V2V, if you are going to deploy that service over the cloud, not using the fog computing, so there is a much delay, and the real time data at that instance will not be showing with us. So that is giving us the motivation that, okay, to kill this problem, we should go to some other solution. As I always say to my student that in the technological revolution, if you are providing solutions, and based on those solutions, you are introducing some new problems as well. So initially the cloud providers, they solved one problem for the computing, but in fact, some new applications arised, and those applications were giving some more challenges. So thus, I think it will continue forever as we are introducing some new solutions, and based on the new solutions, there will be some new problems. So we have studied the IoT applications, how IoT works, and what is fog, and now coming towards the SDN, how SDN supports all these different things. Because as you can see that in the traditional networks, because this is a big motivation for the SDN, why we are moving towards the modern paradigm as compared to the previous paradigm, because related to the networking industry, you know that designing of switch, designing of routers, designing of IPS, IDS, and they have their own operating system, they have their own data plane and control plane, and they are tightly bounded together. So that is a big paradigm shift for the current era of networks, current era of IoT, current era of AI, that old technology will not work. As you can see that we have the control plane and data plane. For the sake of understanding, control plane is the brain, the person, or the authority to give some instructions, and the data plane is just to obey those rules. So in the traditional networking paradigm, we have these control plane and data plane together, and they are distributed, and they are all the times they are tightly together. For example, if you are going to upgrade this system, so definitely you are just upgrading this system. You are not even touching this. And so it means that in each and every entity you are facing two things. One is called the control plane and another is called the data plane. And here you can manage these from some remote area. The problem in the traditional networking mechanism, please relax, I will definitely integrate the concept of SDN with the IoT and fog, but just to perhaps some background knowledge, some background ABC about these three. So we have closed equipment. It is impossible for us to change the operating system of Huawei or Juniper or Cisco because it is closed equipment. And another thing is they have very stringent policy for their protocol standardization, and without their support, without their engineers, it is almost I will say difficult to innovate because it is not open source. So these are the problems, and the network industry was facing these problems. So that's why they shifted to some paradigm where they can easily innovate. As you can see that this is the traditional switch, and in this traditional switch you can see that this is the control plane and this is the data plane. So control plane is responsible for all these building information, storing information and forwarding decision, and this data plane is going to obey those different rules, and we have some different ports that are connected to the outside world. So just imagine if you install 100 switches, you will be having 100 data plans and 100 control plans. So then there was a concept back in although the separation of concern of this control plane and data plane is not a new thing. It was not just coined back in 2008 by Martin Casado and their friends, but it backs to the 1980s, but at that time it was not the proper time to launch the concept of SDN. The same thing happened to the the OSI model and the TCP model. So the separation of concern says that, as you can see, that to separate or decouple, if we say in the ONF definition that SDN is a new paradigm where the control plane is responsible to modify the data plane, and where the data plane will obey all instructions and commands from the control plane. So this is the overall philosophy of the SDN. Now, if someone is going to integrate some new solution, that you can say that will be the hybrid solution, but not specifically pure SDN, because on the website of the ONF, you will see that as in SDN environment, so this is a decouple approach. As you can see that control plane and data plane are totally separate. They are physically separate, not just on the software module. For example, module 1, module 2, no, they are physically separate entities. So one is the data plane. So in that sense, we can say switches are the data plane, and the control plane where your application resides, where your operating system is there, that we say network operating system. So those two are separately, they are totally independent and they work together. So the control plane is definitely the logic, and the data plane is to obey all those different instructions or open flow rules, etc., etc. This is the broader architecture of the SDN, and here we have different applications, and here is the control plane. This will be some physical entity, and this physical entity will have some operating system, maybe Open Daylight, maybe ONS, ONOS, maybe RIO controller, NOx controller, POX controller, and here we have the forwarding agent. And the working mechanism is this one, that okay, this is logically centralized. Now this is your control plane, and from this control plane you are managing all the different data planes. As I said, that when you are introducing some new solutions to the industry, so definitely you are introducing some new problems as well. Here we see that there is a big problem, and that problem is the single point of failure. And there is another problem that, for example, there can be a DDoS on this. So this is just one entity. If this brain fails, then definitely your network will not work. Of course, there is another point, that is there are many challenges related to this single point of failure, and there are some solutions as well. For example, distributed controllers. But when we are introducing distributed controllers, they are introducing new challenges of the complexity of the open flow protocols and their configuration. Here, as you see that I already explained, this is our traditional computing, and this is our modern SDN. And inside the open flow enable switch, that works inside the open flow enable switch. So we have the open flow enable switch, and in that switch we have some flow tables. Those flow table can be hardware flow table or software flow table, and in that flow table we have some entries, and in those entries we have some different fields. So right now Open Flow Protocol specification 5 point above, I think 1 or O, that encompasses 48 tuples. 48. Here we show that so 1, 2, 3, 4, 5, but that contains 48 tuples. It means you can have the combination of 48 tuples. Here, if you say that this is the action encounter, so you are just playing with 2 fields, but in that case you are playing with 48 fields. Means here it is very easy. For example, you can say that if this is the MAC source, and this is the ETH type, and this is the IP destination, and this is the some other field, then do this. So this is one rule. Another rule can be this is the VLAN ID, then do this. This is another rule. So you can think of 48 different combination. In the 48 combination, there can be, I think, more than, I think it's too big amount. How many? It's too big amount. More than millions of the flow rules can be installed inside that single switch, subject to availability of that flow table. So you can think that how the open networking and the open source mechanism gives us the possibility to innovate. Now you don't need to rely on some Cisco, you don't need to rely on Juniper, you don't need to rely on other vendors, although they have their own philosophy that, oh, we are very extreme good in these things and we have 60 years or 70 years of experience. But definitely, marketing is always there. But the open source community says that we can innovate on our own selves. We just buy a server, we just buy some x86 or x64 switch, and we will deploy our own application and we will design it on our own way. You don't need to buy some router, you don't need to buy some IPS, because you can configure all those things through these 48 tuples. And this is another slide. As you can see that here layer 2 switching, here layer 3 switching, then MAC destination based switching, then IP destination based switching, and so on. So you can have, through incorporating the SDN philosophy, you can have the layer 3 switching, you are having the IPS, you can have the firewall, even not buying specific firewall, but you can make all those network devices through the concept of SDN. And this is just the hybrid approach, that it's not feasible for all of us just to start everything, multiply by 0 and buy new things. But these are different architecture. For example, if you are having already switches in your organization, so you don't need to do this scratch. You can there is a possibility of the hybrid architecture, and there is a possibility of the centralized architecture. So now we are coming towards the integration of the SDN in those fog-based IoT. Now we are in the real state, because the previous things we just discussed the SDN, we discussed the fog, and we discussed the IoT. So now we are going to integrate that how SDN can support all these different applications. For example, here without SDN, it was not with you, this control was not with you. But with SDN, now you have this device there. These devices there can be your servers, these can be your some IoT devices deployed for agriculture, or these can be some sensors that are deployed in some hospital, and then you can have this communication. And above, you are having the SDN controller, and that SDN controller definitely that will work for you, because we need operating system. And based on that operating system, we have some different applications. As you can see that this is the IoT application. So this IoT application can monitor the traffic system. This IoT application can be deployed for some smart city, or this IoT application can be deployed for some hospital, etc. Another slide, this is a research work of another student. So you can see that IoT nodes, and we have some IoT gateways, because the IoT nodes, they are talking to each other with different protocols, maybe ZigBee, maybe some other protocol, and it is impossible, or at least right now it is not possible for the ZigBee device to directly communicate with the OpenFlow enabled switch. So that's why there is a gateway, IoT gateway, and that gateway is the bridge between the switches and the IoT devices. And then this is your SDN controller. So the SDN controller will have your application, and this application is totally open source, and it is totally based on your desired policies, etc. This is another one. IoT devices, and here another cluster we have other IoT devices, and these IoT devices are sending data to the SDN switches, and we have SDN controller, and we have another master SDN controller. So it depends on the application, it depends on the topology, that which topology you need for your organization. Another one, almost the same concept but in a different way. So we have SDN controllers, we have these devices, we have wireless sensor networks. So the point is this, that how SDN integrates these different topologies, these different technologies, and these different architecture, and how SDN supports us in all these different scenario. Almost I have showed this in the previous slide. So SDN is revolutionized the networking. It is of course not that much prevalent in modern industries because of the how to say, you know, the Cisco, Juniper, Huawei, big switches, they are in the networking industry since long time. So definitely it will take time to replace the traditional networking mechanism. And of course there is another beauty, and they have even those Cisco, Juniper, Huawei and other big names, they are making their own devices based on the SDN, and they are providing you that okay, SDN is an open environment, but definitely we are the pioneer in all these things. So if you want to buy, if you want to configure all these things, do it from our organization. So this is all about, definitely because of the time constraint, I tried my best to summarize these three technologies, but definitely it needs lot of time. Thank you very much.